Non-deterministic finite automata can be represented in a simpler form sometimes than deterministic finite automata. But it's important to realize that this does not mean they are more powerful. The term power is of a particular scientific meaning in our field. We discuss automata that can recognize more complicated languages as being more powerful than others. It turns out that the class of languages that maps to DFAs is also the same class that maps to NFAs. In that way, we can convert among all of these things. Given a language, you can find a DFA and an NFA for it. Given a DFA, you can find an NFA. Well, the DFA is an NFA. Given an NFA, you can find a DFA that represents it as well. All of these are mathematically congruent ways to represent the same idea, that of a language and a computer. Let's not lose sight of that in this jumble of arrows and circles. What we are really after here is indeed nailing down in a formal way what is it about processing language that we can call computation. We have formal languages and we have automata. Both of these work together to model what we mean by computing. In the next two videos, it's going to be pretty mathy, pretty algorithmic. What we're going to do is worry about exactly those transitions. We want to take a expression in one form and convert it to something in another form. So we're going to run through two algorithms in these two videos and just take you through that. And the long-term takeaway from all of this is not that you'll be sitting there as a software developer and need to run through these algorithms to convert an NFA to a DFA or whatever. The takeaway is that by doing this work, you will develop yourself intellectually to the point where you more deeply understand what it is that we're talking about here, what it is that we mean by formal representations of languages and computing. This is also an introductory course to the theory of computation itself as its own discipline. We have another course after this one that is an elective, if you so choose to take it, that takes a much more mathematical dive into all of this. So those of you who are double math majors or who are really interested in this, the theory of computation is a tremendous area. It's where computer science started, and this is the intro course to that whole sequence. For those of you not interested in doing that, and I fully understand you not wanting to spend a bunch of time proving math theorems, but for those of you who aren't interested, this is still really great because it helps you understand part of the field that you can then read from. You can consume this information. You might not be producing all of this, but you'll understand what people are talking about when they discuss an automata or a formal language or a state machine. This broadens your intellectual bearing with respect to your chosen field of computer science. So I just encourage you for this last couple weeks here to stay the course, stick with it, and I promise you that all of the energy you put into it will be realized as a tremendous gain a year, 2 years from now, in ways you won't even realize, in ways that you can't even understand. I have a mathematics bachelor's and master's degree, and I just am constantly using that. I'm not proving theorems every day, but my understanding of society and psychology and absolutely everything that I engage with in my life is made stronger and is informed by that sort of background. Just the way we can precisely see things as human beings is really important. So I really emphasize this. A lot of people express an alternative opinion about this material here when you get to this point in this course. I've taught this in the classroom before, and what they want to be doing is writing programs, right? They want to get back to the software engineering courses. They want to develop the sorts of software that they'll be using at Cerner, say. And I can understand that, and I'm not saying that that's not an important thing to try to do, but that's not what every single course here is about. There are courses about that, but not all of them. And part of your formation, not just training, part of your formation as a computer scientist here at Truman is is seeing some of this, is engaging some of this. So there you go. Just trust us. This is a this is a standard course that most computer science programs have in one form or another. In fact, we actually do a little bit less of the theory of computation side because we had all the formal logic in addition to it. If you're at all intellectually curious about your field, this is just fascinating. Just enjoy the ride, and we'll get to a really good place. So okay, enough pep talk. Let's get to the computing. So the idea here is that if I have one of these regular expressions, I can create a finite automaton out of it. I can have a finite automaton that can recognize that expression. So how do you do that? In the previous video, we did it by the seat of our pants. We used our mathematical understanding, however developed that may be for each of us, in order to do this. What is presented here is an algorithm. So the algorithm is here for two purposes. One, if you want to use it, you can. We're not going to be doing this problem enough. This is not a integration by parts level computation that you have to get super good at. So the main reason to see this as an algorithm is to understand that it is programmable, that this calculus that we're working with here is something that can be turned over to a program and a lot of progress made. Just like in the formal logic portion, where we could have our proofs generated computationally, we can do some work here in that regard as well. We come up with a regex for some sort of text that we want our program to engage, and we want to design an automaton and implement it in our programming language so that we can do this. Well, we have ways to do that. We have ways to, if you as a programmer specify what the regular expression is, the program can generate the automaton. And here we're just representing these automata as circles and arrows, but we can program them. Right? You can make this a state machine inside computer code. Right? You'll have a variable that represents what state you're on, and then you just have a big switch statement basically. It says if I get this input, then I go here. If I get this input, then I go here. That tracks the state as represented as a variable inside your program. And this is how we can work with some of these things. So it's not just math on paper. It will come back and you can do programming with it. And again, the compiler itself is the canonical example of this. And when you take a compiler's course, you'll see all of this again in a more directly applied setting. Okay, so we begin this algorithm by having the start over here, and then the regular expression is going to be in between, and then we have the final state. This is a pretty general description of what we're looking at here. So what we have here are three rules that can apply for each of the different combinations, different operations that we have in our algebra of regular expressions. Remember, regular expressions form an algebra in a technical mathematical sense. We're not going to get into that too much. If you take an algebraic structures course, then I encourage you to revisit all of this from that perspective. So if we add two components together, two terms together, then we end up with this, right? Because the add means or. So if I'm in state I can get to state J by either going on S or by going on R. If we multiply together, this means and. So I have to go R and then I have to go S. And if I have the star, then that means I can have any number of R's. So I have this state in between where R just keeps looping. And remember, the lambda edges are edges that are consumed without reading a input symbol. So that means I'm in I and I can go to R if I happen to get one, but I could also just go straight to J. Since these are linked by lambda edges, if I'm in I, I'm automatically in J as well. Remember, for an NFA, we don't have just a single state that we are in at any moment. We have a distribution. We've got a set of states that we can be in. And that's what these lambda edges represent. And the R here then says I can have any number. If you had to have at least one, then you wouldn't have these lambda edges. You wouldn't have the first lambda edge. You'd have one R to get to here and then any more that you require. And then the second lambda edge would get you to J. So look at these, like look at these pictures and make sure you can understand what they're doing. Relate the algebra of regular expressions, relate what these operations are over here to what we're seeing in the diagram of this one. Let's run through an example. we've got AB star plus BA. So the first thing we see is this plus sign here. So this is the rule for plus, which means that we're going to have our AB star on one of these arrows and our BA on the other arrow. So now we have to unpack what each of these is. So the star one, you see that the R star transforms into this. So down here we have the AB star. So we're applying this rule over here to unpack the lower arc here to give us the AB star. And the reason that the AB looks like this is because using the multiplication rule, I see that I have this. In this case, I and J are the same state. So I and J are both this state. So if I have A, B going back, then I have A going to this middle state and then B going back to the first state. But this here, this construct down here is an application of the multiplication rule. And the fact that I've replaced my AB star arc with this construction is an application of this rule. So you can see where a computer program can do this. All you have to do is cycle through your entire regular expression, building up the diagram as you go. You can do this by hand, you can do this by computer program. It might be interesting to compare your exercises from before, when you were just doing it in an ad hoc manner, to a formal application of this algorithm. And keep in mind that there's not necessarily one exactly correct answer in this business. You may have a situation where you can have multiple different diagrams that are equivalent machines, right? Of course, right? You should be understanding enough about mathematics at this point to understand that there's some sort of equivalency and there's a transformation and there's going to be theorems and rules about which one is equivalent to which one. In fact, the next section is going to be on minimizing these, creating efficient automata, which is going to be about looking at different ones that are more and less complex and deciding if they're equal to each other. All right, and then we finish it off by using the multiplication for the upper arc. So R times S, B times A over here. So go back through this, understand how we exploded each of these areas, and we just kept making the diagram more and more complex as needed. We started with the plus in the middle to give us this state, these two outer states, and we've also finished now with the final state in there. And we had this, we developed it, and then we did the star, and even within the star we've got another multiplication, and then we have the multiplication for the BA. So run through this algorithm, make sure that you relate the elements of these diagrams to what's going on in the regular expression. Regular expressions are of incredible importance in computer science. You'll see them again, and all of the work you do here now is helping deepen your understanding and your engagement with this important idea of regular expressions.